Welcome to The Explainer. Today, we're diving into the world of biostatistics. I know, sounds a little intimidating, right? But we're going to break it all down so that you can look at any medical study and know exactly what's going on.
You know those headlines you see all the time? A new miracle drug, a groundbreaking treatment. But how do you know if it's for real? Well, it all comes down to the statistics behind the claim. And today, we're going to crack that code so you can separate a real discovery from, well, just random noise.
We're basically going to put on our lab coats and follow a researcher's journey. We'll start with a simple question and see how it gets transformed into a real scientific conclusion, step by step. Ready? Let's get into it.
Okay, so first things first, before you can even think about collecting data, you've got to be crystal clear about two things: what exactly you're testing and what exactly you're going to measure.
So at the heart of any experiment, you've got these two key players, variables. First, there's the independent variable. Think of it as the cause, or the one thing you, the scientist, are changing. For our little plant experiment, that's our special grow-fast fertilizer. Then you have the dependent variable. This is the effect. It's what you measure to see if your change did anything. Its outcome depends on the independent variable. And in this case, that's the final height of our plants. Simple enough, right?
Okay, so we're measuring height, but how are we measuring it? If we get out a ruler and measure in centimeters, that's what's called parametric data. It's got a consistent scale, it's precise. But what if we just ranked them? You know, this one's small, this one's medium, and this one's tall. That's called non-parametric data. It's more about counting or putting things in order. Both ways are totally valid, but the kind of data you collect determines the kind of math you can do later on.
All right, fast forward. We've done the experiment, we've got all our plant heights written down, now what? Well, the first step is to just look at the data. We want to get a feel for its overall shape, what statisticians call its distribution.
In a perfect world, if we plotted all our plant heights on a graph, they'd look like this, a beautiful, symmetrical bell curve. This is the famous normal distribution. See how most of the plants are right there in the middle, around the average height? And you have fewer and fewer plants that are super short or super tall out on the ends. This classic shape is actually a really big deal because a lot of powerful statistical tests assume your data looks kind of like this. But let's be real. The world isn't perfect, and neither is data. A lot of the time, it's lopsided or skewed. Take a look at the image on the left. That's a positive skew. Most of the data is bunched up on the low end, but you have this long tail stretching out to the right. The one on the right is a negative skew, the exact opposite. A great real-world example is income. Most people in a city might earn a similar amount, but then you have a few billionaires whose income would pull that tail way out to the right, creating a positive skew.
So that leads to a problem, doesn't it? If the data is all lopsided, what's the typical value? How do we find the center? You can't just pick one number. Luckily, researchers have a toolkit with 3 different options to nail down that center point.
And here's where it gets really clever. Each of these measures deals with those extreme values, those outliers, in a different way. The mean is what you probably think of as the average. Just add everything up and divide. But its weakness is that it gets totally yanked around by outliers. If one of our plants is a freakish giant, it's going to pull the mean way up. But then there's the median. The median is just the middle number in the list. It literally doesn't care about that giant plant at the end. It's focused only on the middle. That's why it's so useful when data is skewed. And the mode? That's just the number that shows up most often. Easy.
Okay, so we've looked at our data, we found the center, and it looks like, hey, the plants that got the grow-fast fertilizer are taller on average. But here's the million-dollar question. Is that difference real, or did we just get lucky with the seeds we picked? To figure that out, we have to formally test our idea. It's showdown time.
And this brings us to maybe the single most important idea in all of research statistics, the null hypothesis. You can think of it as the ultimate skeptic. Its default position, its starting assumption, is that our fertilizer does absolutely nothing. It says, nope, that difference you're seeing in plant height, that's just random luck, pure chance. We call it H0.
So our whole experiment, its entire purpose, is to try and prove that skeptic wrong. We're on a mission to gather so much evidence to show a difference in height so big that the "it was just random chance" excuse starts to sound completely ridiculous. If we can do that, then we get to do something very satisfying. We get to reject the null hypothesis.
All right, so we run the numbers, we do the tests, and we have a result. But how sure are we? How confident can we be that we made the right call about rejecting that null hypothesis? This is where statistics gets really, really interesting.
You've definitely heard of the p-value. It's everywhere. But what is it? Think of it this way. The p-value is the probability of seeing the results we saw if the null hypothesis was actually true. So it's the probability that we got these results by pure, dumb luck. The magic number everyone looks for is less than 0.05. A p-value below that means there's less than a 5% chance that our findings are just a random fluke. And that's when scientists declare a result statistically significant. It's often the star of the show in news headlines, but trust me, it does not tell the whole story. Because here's the thing, even with the tiny p-value, we're never 100% sure. Science deals in probabilities, not absolute certainties. And whenever you're making a decision based on probability, there's always a chance you could be wrong. In fact, there are two huge ways you can mess this up.
And this chart lays them out perfectly. On one hand, you have a type 1 error. This is a false positive. We get all excited, we reject the null hypothesis, and we announce that our fertilizer works, but in reality it doesn't. We got fooled by chance. It's like your smoke alarm blaring when you're just making toast. Then there's the type 2 error. This is a false negative. Our fertilizer actually does work, but our study wasn't sensitive enough to pick it up. This is maybe even worse because we've missed a potentially important discovery.
So how do we guard against that dreaded type 2 error, missing a real effect? The answer is statistical power. Think of power as the sensitivity of your experiment. It's the probability that your study will actually detect a difference if that difference is real. Researchers usually want their study to have a power of 80% or higher. That means they have an 80% shot at finding a real effect. And how do you get more power? The simplest way is to use more plants, a bigger sample size.
Okay, let's imagine we nailed it. Our p-value is super low, our study had tons of power, we confidently rejected the null hypothesis. We proved it! Our fertilizer works. High fives all around, right? Well, hold on, because now we have to ask what might be the single most important question in all of this.
And if you remember one thing from this whole explainer, make it this. Just because a result is statistically significant doesn't mean it's clinically or practically significant. All statistically significant means is that the result probably isn't due to random chance. It says nothing about whether that result is actually meaningful in the real world.
I mean, think about it. If you have a huge study with, say, 100,000 patients, you could prove with statistical certainty that a new drug lowers blood pressure by 1%. The effect is real, it's not chance, but is a 1% drop actually going to help anyone? Is it worth the side effects? Probably not. It's the same with our fertilizer. What if we prove it makes plants taller by an average of 0.5 centimeter? Is any farmer going to spend money on that? No way. And that right there is the final piece of the puzzle. It's the question every good researcher and every smart reader of research, like you, needs to ask. The data might show an effect, but does that effect matter? Is it big enough to make a difference in someone's life? So next time you see a headline, look past the p-value. Ask about the real-world impact, because that is the difference between a minor statistical blip and a truly life-changing breakthrough.